Welcome to Talk Tensors. This is the deep dive where we try to separate the signal from the noise in the absolute avalanche of machine learning papers hitting the timeline every single week. I am your host, and as always, I'm joined by our resident expert to help make sense of it all.
It's really good to be here. And honestly, avalanche might be a bit of an understatement lately. It kind of feels more like a fire hose of information.
Yeah.
And the pressure is just getting higher and higher.
It really does. It's nonstop. And usually when we look at that fire hose, for you listening at home, you probably notice a pretty clear divide in the industry right now.
Oh yeah, a massive divide.
Right. On one side, you've got the closed source giants, your GPT-4s, your Gemini Ultras. They have the massive compute clusters, the secret proprietary data sets, basically an infinite money glitch.
Yeah, billions of dollars of compute.
Exactly. And then on the other side, you have the open source community. And they're scraping by with what they can publicly find, doing really amazing work, but usually lagging behind on the really hard stuff. Specifically mathematical reasoning. That has historically been the moat.
Right.
Because text generation, sure. Creative writing, open source is right there. Sometimes it's even better for specific use cases. But complex, multi-step mathematical logic, that has absolutely been the playground of the trillion parameter models.
Exactly. Until now, or well, at least until this specific technology we are unpacking today dropped. We are doing a deep dive into a model that is causing a serious stir right now. It is called DeepSeekMath 7B.
And the 7B is the crucial part there.
Right. 7 billion parameters. In the world of modern large language models, that is, it's tiny.
It's extremely small.
That is run on your laptop small, run on a gaming PC small. But the claim here is that this little 7 billion parameter model is outperforming Google's 540 billion parameter Minerva model from just a couple of years ago.
Which is wild.
It is wild. Yeah. And it's nipping at the heels of GPT-4 on actual competition level math benchmarks. It's a classic David and Goliath story, but with vectors and matrices. And usually when we see these claims, I think we have to be incredibly skeptical.
Oh, absolutely. And my first thought when I saw the headline was, okay, where's the cheat code?
Right, exactly.
Because usually when a small model claims to beat a giant, they've either they've trained on the test set, or they're using some massive external calculator tool to do the heavy lifting.
Or they're using a chain of thought prompting technique that's like 5 pages long and runs the model 100 times to vote on the right answer.
Yes, exactly. But that is the skepticism we should always have. But what makes DeepSeekMath interesting, and why we're dedicating this full deep dive to it today for you all, is that they didn't use those tricks.
No, they didn't.
They didn't use external toolkits like Python interpreters to get the score. They didn't use complex voting techniques where you generate 100 answers and pick the most common one. This is pure architectural and data innovation.
So no tricks.
Right.
Just better math. And better math derived from a significantly better process.
I love that.
Because the core contribution here isn't just, hey, here is a set of model weights. It is a roadmap. They are proving that if you combine extremely high quality open web data mining with a novel reinforcement learning algorithm, which we will get into, it's called GRPO.
GRPO, yeah.
Yeah, if you combine those, you can actually close that gap between the massive capital-intensive models and the efficient open source ones.
Okay, let's really unpack this. Because saying high-quality data sounds so easy, but we know it's not.
It is the hardest part.
And GRPO sounds like, I don't know, a sound effect from a comic book or something. But I know it's actually a really clever tweak to how we do reinforcement learning. We just have a lot to cover today.
We do. We need to go really deep because the devil is absolutely in the details of this one.
Okay, here is the roadmap for this deep dive. We are going to break the pipeline down into 4 main parts. Part 1 is the treasure hunt, basically how they found 120 billion math tokens hiding in the messy, chaotic internet. Part 2 is the base model, why they started with a coding model instead of a general language model. That is a twist I did not see coming at all.
It's a crucial detail. It really speaks to the fundamental nature of what reasoning actually is inside a neural net.
Part 3 is the heavy lifting, the algorithm itself. We are going to explain group relative policy optimization, or GRPO. I want to really get into the mechanics of that because it seems to be the key to their training efficiency.
It is.
And finally, part 4, the results and what I'm calling the ARC-SIF paradox, which completely blew my mind regarding scientific papers. And of course, we will finish up with our novel notions segment at the end.
Sounds like a solid plan. Let's dive in.
Okay, let's start with the data. Part 1, the data engine. Now, I have to ask the naive question here just to set the stage for everyone listening. If we want a model to be good at math, why can't we just feed it every single math textbook ever written, all of Wikipedia, and just call it a day?
That's a fair question. It's really a problem of scale and density.
Scale and density.
Yeah, because textbooks are great, obviously. But there aren't actually that many of them, relatively speaking, in the context of training a modern LLM.
Right, compared to the whole internet.
Exactly. Not nearly enough to train a model from scratch. You need billions and billions of tokens. And Wikipedia is great, but it's often descriptive rather than procedural.
What do you mean by descriptive versus procedural?
Well, Wikipedia tells you about math, like the history of the Pythagorean theorem, who invented it, what its applications are. But it doesn't always show the messy, step-by-step grinding of solving 1,000 different unique triangle problems.
Okay. It gives you the facts, but not the practice.
Right. It doesn't show the work. So we need the internet. We need forums. We need homework help sites, PDF tutorials, personal academic blogs.
But the internet is incredibly noisy.
It's mostly noise.
Yeah.
If you just train on Common Crawl, which is basically a raw scrape of the entire web, you get cat blogs, recipes, political arguments, endless spam. Mathematical reasoning requires a very specific type of structured logic that is sprinkled extremely sparsely across all that noise.
So it's like looking for needles in a haystack, but the haystack is the size of the moon.
Precisely. And previous attempts, like the Minerva model we mentioned earlier or the Open Web Math dataset, they tried to filter this.
Yeah.
But DeepSeek took it to a completely different level. They built an iterative pipeline. It wasn't just a one-and-done filter. It was a loop.
Okay, walk us through this loop. They call it the data selection pipeline. Where exactly does it start?
It has to start with a seed. You can't find what you're looking for if you don't know what it looks like in the first place.
Right.
So they started with a high-quality seed corpus. Specifically, they used Open Web Math. This is a collection of known, vetted, good mathematical content. It's got the latex formatting, the proofs, the rigid logic structures.
Okay, so that's the gold standard. That is the reference material the system uses to learn.
Right. They take that gold standard. And step 2, they train a model called fast text. Yeah, think of fast text as a very lightweight, very fast classifier. It's not a full large language model. It's a much simpler machine learning model that just looks at word vectors. They trained it on the seed data, so it essentially learns the scent of math.
The scent of math, I like that.
Yeah, it asks, what does a math page actually look like? What tokens does it use? It looks for words like theorem, proof, integral, but crucially, also the structural markers.
Like what?
Like latex dollar signs. You know how math is formatted online using latex equations? Fast text learns to flag those specific formatting quirks.
Okay, so you basically train the sniffer dog on the exact scent of the gold.
Exactly. Then, step 3, they unleash this fast text model on the entirety of Common Crawl.
Wow.
We're talking about 40 billion HTML pages here. The sniffer dog just runs through all of them at blistering speed and flags anything that smells vaguely like math.
That is a staggering amount of data to process. And fast text is actually fast enough to do that economically.
It is. That's exactly why they use it instead of a transformer model for this step. It's incredibly efficient. But here is where they get really clever. This is step 4, and I think this is the secret sauce of their whole data pipeline.
Okay.
They don't just look for individual pages. They look for domains.
Explain that, because normally when we talk about scraping the web, we think of it as a page-by-page filtering process.
So let's say the sniffer dog finds a random PDF on a university website, and that PDF is pure, high-quality math. A standard filter would just grab that single PDF, say, good job, put it in the bucket, and move on to the next random URL.
Right.
But the DeepSeek system says, wait a minute, if there was one really good math paper here, maybe this entire section of the website is a gold mine.
Oh, I see. So if it finds a page from, say, mathoverflow.net or a specific professor's subdirectory on MIT's OpenCourseWare, it doesn't just grab that one isolated page. It flags the whole location.
Correct. If a certain percentage of URLs from a specific website are flagged as math by fast text, they'd essentially mark that entire domain for a deep drill. They manually annotate these URLs to dig much deeper into that specific site.
That makes total sense, because they assume that where there is smoke, there is fire.
Exactly. And this allows them to find pages that the fast text classifier might have completely missed on its own.
Like what kind of pages?
Maybe pages that don't explicitly use the word theorem or proof, but are still deeply relevant contextual discussions about a math problem. By grabbing the whole domain, you get the surrounding context.
You aren't just skimming the surface, you're actually finding the veins of ore. It's like if you find a nugget of gold in a river, you don't just take the nugget and leave, you walk upstream to find the mountain it actually came from.
That's a great analogy.
Yeah.
And then comes step 5, which makes the whole thing a loop. Iteration.
Iteration.
The newly found data, all that stuff they dug up from those expanded domains, that becomes the new seed.
Oh, wow.
Yeah. They feed it all the way back into the beginning of the pipeline. Now the fast text classifier has way more examples, much more diverse examples of what math looks like out in the wild.
So it gets smarter.
It gets much smarter. And they run the whole 40 billion page scan again.
So the dog gets better at smelling gold because it has found a bunch of weirdly shaped gold that it didn't know existed before. How many times did they actually loop this?
They ran this loop 4 times.
4 times across 40 billion pages.
Yeah. And by the 4th time, they realized they were getting pretty severe diminishing returns. They had basically scraped the bottom of the barrel of the entire internet for math.
And what was the total haul? Like, how much data are we talking about at the end of this massive mining operation?
They ended up with 120 billion math tokens.
120 billion.
Yes. To put that in perspective for you, that is 7 times the size of the math data used for the Minerva model. And it's 9 times the size of the original open web math seed that they started the very first loop with.
That is a massive, massive expansion. 120 billion tokens of pure math. But I have to ask about quality control here, because if you automate this process across the whole web, aren't you going to accidentally grab a bunch of physics papers or like accounting spreadsheets or just complete nonsense that happens to look like math formatting?
You absolutely will. And that is where the decontamination phase comes in. This is a huge, huge topic in AI right now. Memorization versus generalization.
Right. The teaching to the test problem. Because if the model has seen the literal answer key to the benchmark test during its training phase, of course it's going to get a great score. It's not reasoning, it's just remembering.
Exactly. So they were incredibly rigorous here. They didn't just remove the exact benchmark questions from the training data.
What did they do?
They removed any text segment that contained a 10-gram string that matched any of the benchmarks they were going to test on later.
Wait, a 10-gram string, that means a sequence of 10 words, right?
Yes, exactly. 10 consecutive words or tokens.
That's pretty short. I mean, the quick brown fox jumps over the lazy dog is 9 words. So if a single 10-word sentence in the training data matched a sentence in the test data, they just nuked the whole thing.
They nuked it. They scrubbed it completely.
Wow.
And that is a very strict filter. It virtually guarantees that the model isn't just memorizing specific phrases or standard problem setups. It forces the model to actually learn the underlying mathematical concepts to solve the problem.
Now, there's another detail in this data section that really stood out to me. Most previous attempts at this, they filtered for English only. I think the assumption was that math is universal, sure, but the text surrounding it should probably all be in English just for consistency for the model. But DeepSeek didn't do that.
No, they didn't. They kept the multilingual data.
They kept Chinese math forums, French math papers, Russian textbooks, everything.
Everything. And that turned out to be a brilliant move. It was a feature, not a bug. It actually improved the model's performance across the board, even on the English benchmarks.
Why is that, though? You'd think constantly switching languages would just confuse a smaller 7B model.
Well, it seems that logic is just logic, regardless of the human language it happens to be wrapped in.
Right.
By seeing the exact same mathematical concepts explained in both Chinese and English, the model might actually be learning a much deeper, more abstract representation of the reasoning process itself, rather than just memorizing English word patterns that correlate with right answers.
That makes a lot of sense. Like, a triangle is a triangle whether you call it triangle in English or sanjiaxing in Chinese. The geometric properties don't change.
Exactly. By training on both, the model essentially triangulates, no pun intended.
Nice.
It triangulates the concept itself, completely independent of the linguistic label.
That's fascinating. It really suggests that math is truly a universal language, and the LLM is learning the underlying mathish beneath the human languages. Okay, so we have a pristine, massive 120 billion token data set. That is our fuel. Now let's talk about the engine they put it in. Part 2, the base model.
This is where the decisions get really counterintuitive.
Yeah, I saw this in the notes and I had to double take. They didn't start with a general language model. They didn't just take Llama 2 or something and teach it math.
Yeah.
They initialized the model from DeepSeek Coderbase v1.5, a coding model.
Yes, a model built specifically to write software.
Why? I mean, I know programmers are generally good at math, but why start with a programmer AI to build a mathematician AI?
The researchers had a very specific hypothesis going into this, and the hypothesis was simply code equals reasoning.
Code equals reasoning. Look, I want to push back on this a little bit because writing a simple HTML script or a basic Python web scraper isn't the same as solving a differential equation. How does learning to write Python help an AI learn to do calculus?
It's a fair pushback. But it's not about the content of the code. It's about the structure of thought required to generate valid code.
Structure of thought.
Think about what a coding model is forced to learn during pre-training. First of all, it has to learn incredibly strict syntax. If you miss a single parenthesis or a semicolon in C++A, the entire code crashes. It fails completely.
Right. There's no room for ambiguity.
Exactly. Natural language is sloppy. You can misspell a word, and I still know what you mean. Compilers don't forgive. Second, a coding model has to learn long-range dependencies.
Give me an example of a long-range dependency for everyone listening.
Sure. Let's say you are writing a script and you define a variable, x equals 5, way up at line 10. Then you write 100 lines of completely different logic. Then down at line 110, you finally call that variable x inside a new function.
Okay.
The neural network has to remember what x is, what data type it is, and exactly how it is allowed to interact with the current function across a huge gap of context. It has to hold that specific state in its memory perfectly.
Okay, I see that. And how does that translate to math?
In a complex mathematical proof, you state a lemma at the very beginning. Then you do 3 pages of complex derivation. And then you finally apply that initial lemma to close out the proof. It is the exact same cognitive muscle. You're holding a truth state and applying it precisely later on.
So the fundamental logic circuits that are formed in the neural net by learning to code, they map almost one-to-one with the logic circuits needed to do advanced math.
Exactly. Plus, code is highly procedural. It is entirely step-by-step. If this condition is met, then do that. While this statement remains true, repeat this loop. That is the very essence of algorithmic thinking, which is exactly what solving complex math problems requires.
Okay, that conceptually makes a lot of sense. But did they actually prove this in the paper, or is this just a really elegant theory they had?
Well, they proved it. They ran a beautifully simple experiment to test it. They compared 2 completely different training pipelines.
Okay.
Pipeline A was the standard approach. Train a base model on general data, like books and news articles, and then fine-tune that general model on the math data.
Right, that's what everyone usually does.
And pipeline B was their hypothesis. Train a base model on code data first, and then fine-tune that coder on the math data.
And pipeline B1.
It wasn't even close.
Yeah.
The code training significantly boosted mathematical reasoning across every benchmark. But there was a catch.
There's always a catch. What happened?
They found that if they trained the model exclusively on code and then sharply switched to training it exclusively on math, the model suffered from what we call catastrophic forgetting.
Wait, it just forgot how to code entirely?
It basically forgot how to code. And strangely, as it lost its coding ability, it also lost some of its general reasoning ability. It became way too over-specialized in just math syntax.
Oh, wow. So how did they fix that?
They realized they couldn't just do a hard pivot. They found the sweet spot was a mixed training stage. They mixed the code tokens and the math tokens together in the final pre-training phase.
So they fed it a diet of both simultaneously.
Right. This kept those coding neurons active and firing while it was simultaneously building the new math neurons. And the synergy between those 2 domains created a much more robust, generalized reasoner.
That is super elegant. Okay, so we have the data. 120 billion pristine tokens.
Yep.
We have the brain structure, initialized on strictly logical code. Now we need to actually train it to be helpful. And this brings us to part 3, the innovation, the heavy lifting of the paper.
Yes. GRPO, Group Relative Policy Optimization.
Now we really need to slow down here and break this down clearly for the audience, because reinforcement learning, or RL, is how we take a smart base model and actually make it useful and aligned.
Right.
The standard way that basically everyone does this right now, OpenAI, Anthropic, whoever, is something called PPO, Proximal Policy Optimization. Before we get to GRPO, what is the fundamental problem with PPO? Why did DeepSeek feel the need to invent a completely new algorithm?
The core problem with PPO is weight. It is incredibly heavy on GPU memory. Yes. To run a standard PPO training loop, you typically need to load 4 distinct models into your GPU cluster at the exact same time.
4 models. But I thought we were only training one AI.
You are only training one model, which we call the policy model. That's the one actually generating the text. But to train it safely using PPO, you need a reference model.
What does that do?
It just sits there to make sure the AI you're training doesn't change its behavior too radically too fast. It acts as an anchor. Then you need a reward model.
Right, to judge if the answer is good or bad.
Exactly. And crucially, you need a 4th model called the critic model. Sometimes it's called a value model.
Okay, what does the critic do that the reward model doesn't?
The critic's job is really tricky. It has to estimate the value of the current state of generation. It basically looks at what the model is typing right now and predicts, given what has been written so far, how likely is this exact path to result in a high reward at the very end of the answer.
So it's predicting the future score while the model is still thinking.
Yes. It is a prediction of a prediction. And to do that with any level of accuracy for complex math, the critic model usually has to be exactly as big and complex as the main policy model itself.
Oh, wow. So if I have a 7 billion parameter model I want to train, I need an entirely separate 7 billion parameter critic model running alongside it just to train it.
Exactly. You are literally doubling your baseline memory requirements and your computational overhead. If you're trying to train a massive 70 billion parameter model, you suddenly need a GPU cluster twice as big just to hold the critic in memory. It is insanely expensive and very slow.
Enter GRPO. How does this new method fix the memory bloat?
GRPO essentially acts like a brutal corporate budget cut. It fires the critic.
It fires the critic. I love that framing. But wait, if you fire the critic model entirely, who is judging the real-time performance? If the AI writes a math proof, how does it know if it's actually doing a good job without the critic guiding it?
The group judges, the peers.
Explain the mechanism. How does that work?
Here is the exact mechanism. For every single math question in the training set, GRPO doesn't just ask the model to answer it once. It asks the model to generate a group of outputs. Let's say it generates 64 different unique attempts at solving the exact same problem.
Okay, so the model tries 64 times in parallel.
Right. And some of those answers will be perfectly right, some will be totally wrong, and some will be technically right, but use a really weird, inefficient, rambling method. GRPO then takes all 64 of those attempts and uses the standard reward model to score them at the end.
Okay.
It then calculates the statistical average reward of that specific group of 64.
The average score.
Yes. And then instead of needing a complex critic to predict value, it simply judges every individual answer strictly relative to that group average.
Oh, so it is literally grading on a curve.
Exactly. It's grading on a curve. If an answer gets a score that is higher than the group average, it gets a positive reinforcement signal. The algorithm says, hey, do more of whatever you did here. But if an answer is worse than the average of its peers, it gets a negative signal. Do less of this.
But wait, let me hit you with a skepticism check here.
Go for it.
If I fire the critic model, isn't that inherently unstable? Like, what if the model is just terrible at a specific problem and all 64 answers it generates are total garbage? If the group average is 0 and one answer gets a slightly better 0, aren't you just positively reinforcing garbage?
That is a highly perceptive question, and that is exactly the danger. And that's exactly why the reference model concept still exists in the background. They use a KL divergence penalty to ensure the model doesn't drift into absolute madness. But primarily, to your point, yes, you absolutely need the base model to be somewhat competent before you even start GRPO.
Ah, okay.
If the model can't get the answer right even once out of 64 tries, GRPO fails. But assuming the pre-trained base model can solve at least some of the problems some of the time, the variance in those 64 tries gives you a perfectly clean mathematical signal to learn from.
Okay, so let me make sure I'm getting this. The critic isn't a massive, separate, memory-hogging neural network anymore. The critic has simply been replaced by the statistical average of the model's own real-time attempts.
Precisely. Mathematically, the paper proves that the mean and standard deviation of the group's scores serve as an incredibly stable baseline to calculate the gradient. You don't need a separate all-knowing neural net to tell you the absolute value of an answer. You just need to know if you are performing better or worse than your own current average capability.
That has to save an unbelievable amount of compute memory.
Massive amounts. You're cutting the heavy lifting almost in half. And because you saved all that VRAM, you don't just pocket the savings. You reinvest it.
How so?
You use that freed up compute to generate even more samples, to make that group of 64 even larger, maybe 128 or 256. Or you use it to increase the overall batch size, the training run. It makes the entire pipeline orders of magnitude more efficient.
Now, does this grading on a curve work for the step-by-step reasoning stuff? Earlier, we briefly mentioned something called process supervision.
Yes, and this is a vital distinction in the paper. They distinguish very clearly between outcome supervision and process supervision.
Let's make this really concrete for the audience. Give me a simple example of the difference.
Sure. Let's say the math problem is simply solve for x. 2x plus 5 equals 15.
Easy. X equals 5.
Right. Outcome supervision only cares about checking the very final answer. Did you output x equals 5 in the very end of your text? If the model says x equals 5, it gets a full reward. If it says x equals 4, it gets 0. It is purely binary.
Okay. It doesn't care how you got there. You could have literally just guessed 5 randomly and it would reward you.
Exactly. Now, process supervision, on the other hand, rewards the model at each individual step of the reasoning chain.
How does that work in practice?
Step 1, the model writes, subtract 5 from both sides, so 2x equals 10. The reward model looks at just that step and says, good job. That is a logically correct mathematical operation. Here is a small reward.
Right.
Step 2, the model writes, divide by 2, so x equals 5. The reward model says, good job, valid step, here's another reward.
So it's literally checking the homework line by line, exactly like a middle school math teacher.
Exactly like a teacher. And the authors found that GRPO works beautifully with both methods. But when you combine the GRPO algorithm with rigorous process supervision, checking the steps line by line, that is when you unlock the truly massive gains in the benchmarks.
And I'm guessing because GRPO is so memory efficient by dropping the critic, you can finally actually afford to do this intensive line-by-line step checking on a massive scale without bankrupting your compute budget.
Exactly. Process supervision is notoriously expensive. GRPO makes it feasible for open source researchers.
That is the key takeaway for me on the algorithm side right there. They deleted a massive accepted component of the standard AI architecture, the critic, replaced it with a relatively simple statistical trick, group averaging, and it actually performed better.
It completely challenges the industry dogma that you absolutely must have a value model to do reinforcement learning from human feedback. It simplifies the entire stack.
So we have the huge 120 billion token data set. We have the code-based brain. And we have this hyper-efficient grading on a curve training algorithm. Let's talk about the actual payoff. Part 4, the results. How did DeepSeekMath 7b actually perform in the real world?
The numbers are frankly staggering for a model of this size. Let's look at the math benchmark, and we should really clarify for the listeners, this is the hard benchmark. This is not basic arithmetic.
Right, this isn't what is 2 plus 2.
No, this is competition level math. We're talking AMC 10, AMC 12, AMY level problems, extremely difficult multi-step logic puzzles that stump most highly educated human adults.
The kind of math where I immediately break out into a cold sweat just looking at it.
Exactly. DeepSeekMath RL7B hit 51.7% accuracy on this benchmark.
51.7%. Okay, honestly, to a layman, 51% doesn't sound like an A+, but in context.
Context is everything here. Before this paper dropped, no open source model had ever broken the 50% barrier on this specific benchmark without using external calculator tools to cheat. It actually beat Qwen72B. Think about that for a second.
Yeah.
A 7 billion parameter model beat a state-of-the-art model literally 10 times its physical size.
And how does it stack up against the closed source giants, like GPT-4?
It is rapidly approaching GPT-4 levels. Now, to be fair, it's not beating the absolute latest, most expensive GPT-4 turbo variants with all the extra system prompts, but it is entirely in the same weight class as the initial GPT-4 release, and it rivals Gemini Ultra.
For a 7B model that you can legitimately download for free and run locally on a consumer GPU, that is just absurd.
It really is.
And what about on the easier stuff? Did they test it on GSM-8K? That's the standard grade school math benchmark, right?
They did. On GSM-8K, it hit 88.2%. It basically solved it completely.
Now, there was a very nuanced point in the results section about how the reinforcement learning actually helped the model. You mentioned something in the notes about pass at K versus magic K. I wanted to define these terms clearly because I think they explain what the RL process is actually doing to the model's brain underneath the hood.
Yeah, this is a really important, slightly counterintuitive insight for anyone actually training these models. Pass at K essentially measures potential. It asks, if I give the model 100 tries at a single problem, does even just one of those 100 tries get the right answer?
Okay, so it measures if the model possesses the fundamental capability to solve it at all. If it gets it right once out of 100, it has a high pass at K.
Exactly. Now, MAGE at K, which stands for majority at K, is different. It asks, if I give the model 100 tries, is the most common answer among all 100 tries the correct one? It measures the model's consistency and its robustness.
So pass at K is pure potential, and MAGE at K is consistency.
Right. And the fascinating thing the paper found was that the reinforcement learning, the GRPO phase, it didn't actually increase the pass at K very much at all.
Wait, really?
Really. The model didn't suddenly get fundamentally smarter in terms of knowing complex mathematical concepts it hadn't seen before. Its raw potential remained basically the same as the base model.
So the RL phase didn't teach it any new math theorems?
No, it didn't teach you new facts. But the MAGE at K, the consistency metric, that absolutely skyrocketed after GRPO. The reinforcement learning taught the model to stop making silly, careless mistakes. It essentially aligned the model's internal output distribution. It took the raw, chaotic knowledge the model already possessed and forced it to be highly reliable.
It's like it turned a brilliant but totally scatterbrained student into a highly disciplined test taker.
That is the perfect analogy. The raw intelligence, the actual knowledge, came entirely from the 120 billion web tokens and that crucial code pre-training phase. The RL just came in and disciplined the model to show its work properly and stay on track without hallucinating.
Okay, we have to talk about the ARC-SIF paradox now, because this is the part of the paper that genuinely made me stop reading and go back a paragraph.
Oh yeah, this is the big aha moment of the whole study for me.
We all assume, or at least I completely assumed, that if you want to train an AI to be a genius at math, you feed it ARC-SIF. Because ARC-SIF is where all the actual scientific papers live. That is the bleeding edge of human mathematical knowledge. It is incredibly dense, formal, rigorous math. Logically, it has to be the best possible data to train on, right?
That has been the standard assumption in the field for years. Everyone uses ARC-SIF. Google's Minerva used it heavily. The proof-pal dataset was basically built on it. But DeepSeek actually ran the ablation experiments to test this assumption.
Okay.
They trained test models on just the ARC-SIF data, and they trained competing models on just the messy web scrape data we talked about earlier.
And what happened?
The ARC-SIF data didn't help. In fact, in several cases, training on the most advanced scientific papers in the world actually hurt the model's performance on these reasoning benchmarks.
It hurt the performance. How can the smartest peer-reviewed papers in the world actively hurt a math model? That seems entirely backwards to me.
Let's debate this for a second. Think about human learning. Why do you think a standard high school textbook is much better for teaching a novice student than a postdoctoral research paper?
Well, a textbook actually explains things. It holds your hand step by step. It assumes you are an idiot and don't know the answer already.
Exactly. Now think about the culture of how an academic paper on ARC-SIF is actually written. It is written by an expert, strictly for other experts in that specific niche. It is incredibly concise. It intentionally skips intermediate steps to save space. It uses phrases like, "The proof is trivial and left as an exercise to the reader."
Oh man, I hate that phrase so much. It follows clearly that. No, it doesn't follow clearly.
We all hate it. But for an AI that is trying to learn how to reason step by step, that kind of writing is an absolute dead end.
Right.
The AI desperately needs the steps. It needs the why. It needs the intermediate logical connective tissue. ARC-SIF papers are mostly just the final polished result and a very high-level, dense summary of the proof. They are declarative, meaning they just declare the truth of a statement. They aren't procedural. They don't actually show the granular
What
work.
was a random post on a math forum?
Exactly. A post on a site like Math Overflow, or a tutorial on some university's .edu domain. The author there is usually actively trying to explain a confusing concept to someone who admits they don't understand it.
Right, so they break it down.
They break it down completely. First you do this, and here's exactly why you do it based on this rule. Then you apply this specific theorem to get this intermediate result. That explicit, verbose, step-by-step hand-holding is the exact format the neural network needs to actually learn the process of reasoning.
So ARC-SIF is literally too smart for its own good. It is too highly compressed. The random web data, which is way messier but far more explanatory, is actually vastly higher quality for the specific task of training an AI to reason.
It completely challenges the whole. Higher quality means more academic dogma that has driven dataset creation for years. Higher quality for training an LLM actually means more explicit, not necessarily more prestigious. If you want a model to think step by step, you absolutely have to train it on step-by-step data, not on the highly summarized final results of human geniuses.
That is a profound lesson for for anyone out there building data sets right now, do not just blindly look for the right answers. You have to look for the explanations.
Precisely. It shifts the whole paradigm of data curation.
Now, we have praised this model quite a bit today, but we have to be objective here. It is not perfect. What can it not do? I saw a note in the limitations section about geometry.
Geometry is a major weak point for this architecture.
Why is that? If it can logically solve advanced calculus, why can't it handle basic triangles?
Because it is fundamentally a pure text model. It has zero visual encoders. It does not actually see the triangle. It only sees the word triangle and a list of text-based coordinates.
But isn't geometry at its core just math? Can't you just solve it algebraically with equations?
You can, technically, but so often the easiest path to a geometry solution requires instant visual intuition. You look at the diagram and you immediately know, oh, I need to drop a perpendicular line right here to split this shape. Or you mentally rotate the shape in your head to see a symmetry.
And the model can't do that.
No. The purely text-based description of a geometry problem almost always leaves out these implicit spatial relationships that a human eye processes in a millisecond. The paper explicitly mentions the model really struggles with problems involving ellipses and complex intersecting 3D shapes because it completely lacks that multimodal spatial reasoning.
So until we get true multimodal training, where the model simultaneously ingests the diagram and the text together, geometry is just going to be a hard wall for these models.
Exactly.
Okay, what about few-shot capabilities? How does it handle that?
This is a really interesting limitation. So GPT-4 is an absolute champion at few-shot learning. Meaning, if you give GPT-4 3 examples of a completely bizarre, newly invented type of puzzle in the prompt, it instantly figures out the underlying pattern in context and solves the fourth one perfectly.
Right, in-context learning.
DeepSeekMath is remarkably flat in that regard. It really doesn't get much smarter or more capable if you feed it more examples in the prompt. It is basically just as good at zero-shot, meaning no examples, as it is at few-shot.
So it's a bit rigid.
Yeah. It knows what it knows from pre-training, but it is not dynamically learning on the fly in the context window nearly as well as a massive model like GPT-4. It's a highly specialized math engine, not a hyper-flexible general-purpose brain.
But for a 7B model that costs literally a fraction of a penny to run locally, that is a trade-off I think the community is more than willing to accept.
Absolutely. The efficiency gains are worth the rigidity.
Okay, we have covered the 120 billion token data loop, the code initialization hypothesis, the super efficient GRPO algorithm, and the ARC-SIF paradox results. It is an incredibly dense paper, but the core takeaways are crystal clear. Pristine web data mining plus code-based initialization plus efficient critic-free RL equals a giant slayer.
It is a reproducible formula that I guarantee we are going to see replicated and adapted across a dozen different domains in the coming months.
I completely agree. And speaking of adapting this to other domains in the future, that brings us to my absolute favorite part of the deep dive.
Here we go.
It is time for Novel Notions.
I am bracing myself. What do you have today?
As always, a quick disclaimer for the audience. The following ideas are entirely for entertainment purposes only. We are taking the technical trajectory of this specific paper and wildly extrapolating it to, let's call them logically consistent but outlandish places.
Let's do the first one.
Notion number 1, I call it the jury of your peers training loop.
Okay, walk me through it.
So we established that GRPO works so efficiently because it generates 64 answers and simply grades them against the mathematical average of that specific group, right? It totally removes the need for an absolute ground truth value model. It just needs relative ranking. Better or worse than average.
Correct. That's the core mechanism.
Right now, they're using this exclusively for math, which is a domain where there actually is an objective right answer to anchor it eventually. But what if we applied the GRPO concept to highly subjective fields, like legal arguments or creative writing or even ethical reasoning?
Oh, interesting. Fields where there literally is no objective answer key.
Exactly. Suppose you want to train an open source model to write the absolute perfect closing argument for a complex corporate trial. There is no mathematically correct output. But You could have the model generate 64 distinct variations of that closing argument.
Okay.
Then, instead of a math verifier scoring them, you use an incredibly lightweight heuristic model, or honestly, even a very small, cheap panel of human reviewers on Mechanical Turk to simply rank them relative to each other. Just say, I find this argument slightly more persuasive than that one.
And then the model just optimizes its weights for the consensus of that group.
Yes. The model rapidly learns to optimize for the consensus of the best within its own generation capabilities. It becomes a totally self-calibrating creativity engine. It basically pulls itself up by its own bootstraps. Oh. You don't need to build a massive, impossible God model to objectively define what true beauty or true justice is. You just need a simulated jury of peers to tell you what is relatively more effective.
You know, that is actually not that outlandish at all. It aligns perfectly with a lot of sociological theories on how human culture and law actually evolve in the real world. We refine our art and our legal systems through peer consensus and debate, not by checking some cosmic answer key.
Right.
However, the immediate danger there mathematically is something called mode collapse, or basically extreme groupthink.
Explain how that happens in this setup.
If the model learns early on that the simulated jury tends to favor, say, closing arguments that heavily use emotional appeals about family, it might quickly just start generating infinite slight variations of that exact same emotional appeal, because it's a safe bet that consistently beats the average. Without an external critic model explicitly pushing the system to explore novel, wild ideas, a pure jury system might spiral into incredible mediocrity.
So it just finds the safest, most boring middle ground and stays there forever.
Exactly. But if you tune the temperature of the generation right and force diversity in the 64 samples, you could hypothetically build a DeepSeek lawyer model that deeply internalizes the most mathematically persuasive way to argue, based on thousands of simulated jury trials happening in its own head during training.
Your Honor, my client is completely innocent. And furthermore, my perplexity score is significantly lower than the prosecution's.
Something exactly like that, yes.
I love it. Okay, notion number 2. I am calling this one fractal data mining.
This sounds very sci-fi.
It is directly based on their iterative data pipeline. DeepSeek empirically proved that if you just have a tiny high-quality seed of gold, like open web math, you can use that to autonomously find the hidden veins of gold spread across the entire 40 billion-page internet.
Right, the domain expansion technique.
What if we weaponize that pipeline for dead knowledge?
Dead knowledge? What do you mean?
I'm talking about hyper-niche, culturally forgotten, or effectively lost fields of human study. Let's say 17th century alchemy, or a specific dying indigenous dialect, or highly obscure Victorian steam engine engineering manuals.
Okay, I see where you're going. We
take 50 scanned and translated pages of genuine 17th century alchemy texts. That is our tiny gold seed. We use it to train the ultra-fast, fast text sniffer dog, and then we just unleash it on the entire historical common crawl. We tell it to look for that specific linguistic texture, that specific bizarre vocabulary and structural formatting.
You are literally fracking the internet.
Exactly. We are fracking the internet for the deepest, most forgotten veins of esoteric data. Because current LLMs constantly hallucinate when you ask them about this stuff. They hallucinate because those niche topics are statistically drowned out in the training data by billions of modern Reddit threads and SEO news articles.
Right, the signal gets completely lost in the modern noise.
But if you rigorously isolate that specific domain, heavily annotate the surrounding URLs, and run the DeepSeek iterative loop 4 or 5 times, you could conceivably build DeepSeek Alchemy, or DeepSeek Sumerian.
You could autonomously reconstruct fragmented knowledge bases that are effectively invisible to standard models like GPT-4. You would basically be turning the AI from a general-purpose chatbot into a highly specialized, hyper-focused digital archaeologist.
Precisely. We could systematically resurrect the Library of Alexandria, one obscure niche seed at a time, using their exact pipeline, and put it in a 7B model you can run on your phone.
That is actually a really beautiful thought. And honestly, from a technical standpoint, given how remarkably effective the DeepSeek domain expansion pipeline was for pulling math out of the noise, I really don't see any mathematical reason why it wouldn't work for any distinct, definable domain of human knowledge.
So if anyone out there is listening and builds the DeepSeek Alchemy model, I absolutely want a finder's fee for the idea, or at the very least, a working transmutation circle.
I think we can arrange that.
To wrap this all up, DeepSeekMath 7B is undeniably a massive deal for the open source community. And not just because it got a high score on a test, but because of the meticulous method they used to get there.
Pristine, iterative web data mining. code-based initialization for pure logic structure, and hyper-efficient critic-free reinforcement learning. That is the new recipe for punching above your weight class.
The gap between the trillion-dollar closed labs and the open source community is actively closing, and the giants are definitely looking over their shoulders today. And for all of us learners out there building things, that is the best possible news.
Keep your gradients steady.
And your losses low. This has been a deep dive from Talk Tensors. Thanks for listening.